If there is one concept in this entire course that will immediately change how you write concurrent code, it is this one. The distinction between CPU-bound work and I/O-bound work. Once you understand this distinction, you will understand why dispatchers default and dispatchers.io exist. You will understand why adding more threads sometimes helps and sometimes does not. You will understand why coroutines are efficient for network calls, but not for heavy computation. This is the single most practical performance concept for an Android developer, and most developers have never had it explained clearly. So let us fix that right now. CPU-bound work is work where the CPU is the bottleneck. The processor is actively computing, crunching numbers, transforming data, executing instructions, and it cannot go any faster because it is already working as hard as it can. Examples on Android: passing a large JSON response into objects, sorting a list of 10,000 items, applying an image filter or transformation, running a complex regular expression, encrypting or decrypting data, compressing a file. In all of these cases, the CPU is busy. If you look at the profiler, CPU utilization is high 80, 90, 100% on the core running this work. The thread is never waiting. It is always executing. I/O-bound work is work where the CPU is waiting for something external, a network response, a disk read, a database query, a Bluetooth device. The CPU has nothing to do. It issued the request and now it is just sitting there, idle, waiting for the response to come back. Examples on Android: making a retrofit API call, reading a file from storage, querying a room database, downloading an image, writing to share preferences. In all of these cases, if you look at the profiler, CPU utilization is low, maybe 2, 5, 10%. The thread is blocked, but the CPU is doing nothing useful. It is like a chef who has put something in the oven and is standing there staring at the oven door instead of prepping the next dish. Here is why this distinction is so critical. The solution to CPU-bound problems is fundamentally different from the solution to I/O-bound problems. If your work is CPU-bound, you need more CPU power. You can parallelize the work across multiple cores. You can optimize the algorithm to do fewer operations. But adding more threads than you have cores does not help. If you have 8 cores and 8 threads all at 100%, adding a 9th thread just adds context switching overhead. If your work is I/O bound, more CPU does not help at all. The CPU is already idle. What you need is concurrency, the ability to issue multiple I/O requests simultaneously so they overlap. Well, one request waits for the network, another can wait for the disk, and the third can wait for a database response. You do not need more CPU power. You need to stop wasting the CPU power you have. Now you understand why Kotlin coroutines have two main dispatchers. Default is backed by a thread pool sized to the number of CPU cores. On a phone with 8 cores, this pool has 8 threads. This is perfect for CPU-bound work. You have 1 thread per core, maximizing CPU utilization without the overhead of context switching between too many threads. Dispatchers.io is backed by a thread pool that can grow to 64 threads or more. Why so many? Because I/O-bound threads are mostly idle. They are just waiting. Having 64 threads waiting for different I/O operations costs very little CPU. Each thread uses some memory for its stack, but the CPU can switch between them trivially, because none of them are actually computing. If you use dispatcher's default for I/O work, you block one of your precious few CPU-bound threads with idle waiting. If you use dispatchers.io for CPU work, you create more threads than cores, wasting memory and adding context switching overhead. Using the wrong dispatcher does not crash your app, but it degrades performance in subtle ways. When you are looking at a piece of code, how do you determine if it is CPU bound or I/O bound? The simplest heuristic is to ask, does this code call out to something external? If the code makes a network call, reads a file, queries a database, or communicates with hardware, it is I/O bound. If the code transforms data in memory, parsing, sorting, filtering, encrypting, it is CPU bound. For confirmation, profile it. Run the code and watch CPU utilization. If the CPU is peaked at high utilization, it is CPU bound. If the CPU is low and the wall clock time is still long, it is I/O bound. Some operations are a mix. Image decoding reads bytes from disk I/O bound and then decompresses them CPU bound. In these cases, you want to separate the phases, read on dispatchers.io, decode on dispatchers default. Let me walk through common Android operations and classify them. Retrofit API call I/O bound. The CPU sends an HTTP request and waits for the server to respond. Room database query, I/O bound, SQLite reads data from disk, dished and parsing with Moshi or JSON. CPU bound, the parser is actively reading characters, building objects, or locating memory. Image decoding with bitmap factory, CPU bound. The decompressing JPEG or PNG is heavy computation. File download I/O bound. Writing bytes to disk, recycler view, diffutil calculation, CPU bound, comparing two lists element by element. Protobuf serialization, CPU bound, encoding structured data into a binary format. Shared preferences commit I/O bound, writing to an XML file on disk. Knowing these classifications tells you which dispatcher to use for each operation. In practice, you often chain CPU bound and I/O bound work together. You fetch data from the network, then pass it, then store it in the database. The idiomatic coroutine pattern is with context. You start on dispatchers.io for the network call. When the response comes back, you switch to dispatchers default for parsing. Then you switch back to dispatchers.io for the database write. Each step runs on the dispatcher that matches its nature. The beauty of coroutines is that this switching is almost free. It is just a continuation being dispatched to a different thread pool. No thread creation, no heavyweight context switch, just a task moving from one pool to another. This is far more efficient than creating a new thread for each step. There is a third case for Android, the main thread. The main thread handles UI rendering, touch events, and animation. It must never be blocked. When it runs code, it is CPU-bound. Layout, measure, draw, recomposition are all computation. But it has a hard deadline, 16 milliseconds per frame for 60 FPS. Anything that takes longer causes junk. This means you must keep both CPU-bound and I/O-bound work off the main thread. Move network calls to dispatchers.io. Move heavy parsing to dispatchers default. Let the main thread do only what it must, render the UI. The main dispatcher's main ters, is not a thread pool. It is the single main thread. When you launch a coroutine on main, it runs on the same thread that handles touch events and drawing. Keep it light. Let me highlight mistakes I see constantly. First, running room queries on the main thread. Room warns you about this with an exception by default, but some developers disable the warning. Do not. Even a simple query can take 10 to 50 milliseconds, which is a noticeable fraction of your frame budget. Second, doing JSON parsing on dispatchers.io, parsing is CPU bound. It works, but you are wasting I/O thread pool slots with computation that should be on default. Third, using dispatchers default for everything. Default has only as many threads as CPU cores. If you block half of them waiting for network responses, your CPU-bound work has fewer cores available. Fourth, launching hundreds of coroutines on dispatchers default for I/O operations. The default pool is small by design. You will saturate it with idle waiting. Here is why coroutines truly shine for I/O-bound work. Traditional threads are expensive. Each one needs about 1 megabyte of stack memory. If you want to have 1,000 concurrent network calls, you need 1,000 threads, which is 1 gigabyte of memory just for stacks. Coroutines are cheap, a few hundred bytes each. You can launch 10,000 coroutines that each wait for a network response, and they collectively use a tiny fraction of the memory that threads would. This is because coroutines suspend instead of blocking. When a coroutine hits a suspend point, like a network coroutine hits a suspend point, like a network call, it releases its thread. The thread goes back to the pool to do other work. When the response arrives, the coroutine resumes on an available thread. No thread sits idle waiting. This is why people say coroutines are lightweight threads. For I/O-bound work, this is exactly right. Let me summarize with the framework I want you to carry forward. When your code is CPU-bound, transforming data, computing, parsing, use dispatchers default, and optimize the algorithm if it is slow. When your code is I/O-bound, network, disk, database, use dispatchers.io, and optimize by issuing concurrent requests. Never block the main thread with either type of work. Use with context to switch dispatchers as the nature of the work changes. And when in doubt, profile. Measure CPU utilization. The data will tell you which type of work you are dealing with. This single distinction, CPU-bound versus I/O-bound, will improve every piece of concurrent code you write. Next, we are going to learn how to actually read profiling traces. Not just capture them, but understand what they are telling you.